So we're in section 7.5. And we're a little short on time, so I'm going to go relatively quickly. So, work is, the reason we want to find work is we're interested in how much energy it takes to do various jobs, how big of an engine we're going to use, how big of a pump we have to use. So work ends up applying to lots of different things. Has to do with lifting, pulling, springs, rocket propulsion, filling tanks, so pumping liquids. So those are the kinds of things that we're going to look at when we're using calculus to figure out the amount of work. So if you worked in physics at all, or if you even in physical science, you may have talked about this. If you have a constant force, we have the work done by a constant force, F, moving an object through a distance d, we say work is just the force times the distance that we move. So if our force is constant, we just multiply the force times the distance that we move. And a force, when we're talking about a force, we're talking about something pushing or pulling. So we're pushing, we're pulling, somehow we're moving an object. One important thing to remember, if we're working in the English system, we talk about pounds. Pounds is a unit of force. In the metric system, we use kilograms or grams. That's a unit of mass. But in the English, in the imperial system, we use pounds, which is a unit of force. So, for example, if we have a 50-pound object and we move it 4 feet, the work done on that object is 50 pounds times 4 feet is 200 foot-pounds. So that would be a unit of work. Just multiply the weight times the force is the weight in pounds. Pounds is weight. Pounds is force. So in the imperial system, we just multiply the weight times the distance. In the metric system. So our unit of work is foot-pounds or inch-pounds. Those are the two most common units of work in the imperial system, is foot-pound or inch-pound. In the metric system, unit of work is a dyne centimeter, which is called an erg, or a Newton meter, which is called a joule. And 1 joule, just so you know, 1 joule equals 10 to the 7th ergs. So our unit of force in the metric system is a Newton or a dyne. Those are the most common ones. Yeah, work is energy.
Okay, so I'm just thinking because I know that 4.18 joules is 1 calorie.
Right.
So it's calories.
Right. Sometimes we do in physics, but not a lot. So for a constant force, we're just multiplying the force times the distance. We're interested in when we have a variable force. When our force is variable, then we get to use calculus to calculate our work. So we're adding things up, so we're going to be integrating. So if we have a variable force, our method is I'm going to say that my force is some function of x. So our force varies as I move along the x-axis. We're going to divide the interval over which the force acts. We're going to say it acts from A to B. And we're going to divide that interval into n subintervals. By the time we get done with this year, this dividing into intervals and making subintervals and summing over those subintervals, you guys will be able to recite that argument in your sleep, because we're going to do it for a lot of different situations. So we're going to divide it into n subintervals. In the ith subinterval, we like to use I for our index. In the ith subinterval, the work, we're going to call it the small increment of work. So we're going to say delta W sub I. So that's just the amount of work done in that little subinterval is F at C sub I times delta X sub I. Where C sub I is the force, or F of C sub I is the force at the point C sub I in the subinterval. And what we're doing is we're assuming that we're dividing it into small enough subintervals so that we can assume that the force is essentially constant in that tiny subinterval. So on that tiny subinterval, we're saying that the force is essentially constant. So we're just multiplying that constant force times that tiny little interval over which the force acts. And the force over the entire interval, or I'm sorry, the work. So the work is approximately, if we sum it this way, the sum from I equals 1 to n of our f of C sub I delta X sub I and as we let the subintervals get smaller and smaller and smaller, we can say that the work, I'm going to say as delta X sub I approaches 0, so our intervals are getting smaller and smaller, our work is going to be the integral from A to B of f of x dx. So this is the work done by a variable force moving an object along a straight path from x equals a to x equals b along the x-axis. So our work varies along the axis. So we just sum the force over our interval. And in second semester we will learn how to evaluate, how to figure out what happens if the force moves along a curved path. And we get something that we call a line integral, which are fun to do. All right, so everybody understand the argument. We just divide our interval assume the force is constant, sum over those intervals, let the size of the interval get smaller and smaller and smaller, and we end up with an integral. All right, so we will look at three main kinds of problems when we're calculating work with a variable force. Lifting problems and pumping problems. I guess two main kinds of problems: lifting problems and pumping problems. As you lift something, if the amount of stuff that you lift changes, the amount of force that you have to use changes as you lift it. So we'll do an example of lifting a rope. So if you're lifting a rope off the ground, the more you lift, the heavier it gets. So you have to exert more and more and more force to lift it up as more and more of it comes up off the ground. So let's look at a lifting problem. So our example here is we have a climber, and he needs to haul a 50-meter rope off the ground, and we want to calculate the amount of work it's going to take to pick the rope up until it's fully extended. So we have a 50-meter rope. And we want to know how much work to lift to full extension. And we know that the rope weighs 0.624 newtons per meter. So we want to calculate that at your fancy climbing store, the salesman says that this nice climbing rope tells you that it weighs 0.64 newtons per meter. So you know that. So when you buy your carabiner, you get the right capacity carabiner, so you can take into account the weight of the rope. I'm just making this up. So we want to figure out the amount of work. So let's, for any of these problems, I suggest drawing a little sketch. So here's my rope coiled up on the ground, and our climber is up here. And this is .50 meters. So I'm going to say this is my y-axis. What we're going to do is divide this up into little pieces. So when the rope is extended by y meters, I'm going to call this little interval here dy or delta y. So we're going to divide the rope into small sections of length dy. So we're dividing our rope just like we divided our interval. We're going to divide it into small sections of length. The weight of each small section of the rope is how much it weighs per meter times that little increment of length. So our small increment of force I'm going to call it dF is 0.624 newtons per meter times the length of that rope. And each section of the rope has to be lifted through a distance of y meters. So we have to lift it through a distance y. And y varies from 0 to 50. So the piece of rope that's at the very end, when we fully extend it, it's still touching the ground. So that tiny little piece that's touching the ground doesn't get lifted at all. The piece that's in the climber's hand ends up being lifted the entire 50 meters. So our work is just going to be the integral from 0 to 50 of 0.624 y dy. 0.624 dy is the weight, that's the force that we have to exert lifting the object through the distance y. So we integrate that. Pretty easy integral to evaluate. We just get 0.624 y squared over 2 evaluated on 0 to 50. And we end up with 780 Newton meters. So for lifting problems, our procedure is going to be to find the force increment. That's going to be the weight, usually a weight per unit length times a tiny bit of length. We need to figure out this distance that each small section of whatever it is we're lifting is lifted, and integrate over that. The force times the distance, and we integrate over that. The lifting problems are relatively easy to set up.
That's only lifting something that has like those units where you have.
Right. So, and pretty much anything we lift, because as we lift it off the ground, there's more of it off the ground, so we're lifting more and more weight as we lift it. So pretty much anything we lift is going to involve a variable force. A lot of times in physics we assume, like, in order to lift this 50 meters, somehow he has to get a hold of it. So I guess you would have a string that we would assume has no mass, so that he could lift that up. A lot of times the problem would be like a forklift lifting a chain. So a forklift starts on the ground and it lifts the chain, and as it lifts there's more chain, so we have to figure out the amount of work that the forklift does. And if any of you are into lifting weights, there's actually a lot of like hardcore weightlifter guys will put hanging chains off the ends of their barbells, so as you lift it, it gets heavier. So that's a workout method. All right, the second big type of problem is pumping problems, and these I think are my favorite. So with pumping problems, we are pumping liquids out of or into tanks. So the liquid at the bottom of the tank, we have to move through a larger distance. If the size of the tank varies with the height, each little piece of liquid is going to be a different. If we divide it into pieces, each little piece is going to be a different mass, so a different weight. So pumping problems are nice examples of finding work. So I'm going to give you a series of steps for pumping problems that I think make it easier. You want to draw a coordinate system. Draw a picture with a coordinate system. Doesn't have to be a beautiful picture, but it helps to visualize what's going on. So we want to find the weight I'm going to call it delta F. Weight is a unit of force. Find the weight delta F of a thin slab, and I'm writing slab in thin slab of the liquid. So we're going to divide the liquid into small cross sections. We want to find the work. To lift, I'll call work the delta F. Delta W. Delta W to lift the slab. And then we want to integrate over how far we're lifting. So, as an example of this type of pumping problem, we want to know how much work we work to pump water from a full tank. It's an upright circular cylinder. The radius is 5 meters, and the height is 10 meters. So this tank is full of water, and we want to pump the water out. And we want to figure out how much work this is going to take. Now the reason this is that we have to integrate is the small bit at the top of the tank, we just have to pump just over the top. But at the bottom of the tank, we have to pump that over the entire depth of the tank. So the amount of distance we have to pump the liquid changes as we go down the tank. So that's what makes this. That's what introduces the variable part to this problem. So here's my sketch. Here's my tank, upright circular cylinder. I'm going to put the y-axis right up the center, and my x-axis is here at the base. So there's my coordinate system. The height is we're going to add one other little twist to this problem. We want to pump the water from a full tank. It's upright circular cylinder, and we want to pump to a level 4 meters above the tank. So this tank maybe is underground, and it's 4 feet underground, and we have to pump it to ground level. So we're pumping it up to this level. So this is 10 meters, and this is 4 meters. If I divide this into little circular discs, divide the liquid into little circular discs, I'm going to call this little the height of this little disc, delta y, or the thickness of the disc, and its height above 0 is y. So how far do we have to pump this little thin disc of liquid to get it to 4 meters above the ground? 14 minus y. So the entire depth is 14. This distance here is 14 minus y. So we're pumping each little disc of liquid a distance of 14 minus y units if we set our axis at the base. And we're given one other piece of information in our problem. Water weighs 9,800 newtons per cubic meter. So there's our picture. Each disc of water has a volume of what? What's going to be the volume of this little disc of water? Okay, say it one more time. 5 pi squared? Pi times 5 squared. There we go. So we're going to say that the delta V equals pi times 5 squared, or 25. Pi times 25 times delta y. So that's the volume of this little disk of water. The amount of work to lift that slab is the weight, or the force, the weight of the thin slab is just going to be the volume times the density. So the weight of the slab, delta F, is 25 pi times 9,800 newtons per meter cubed. And we get 245,000 pi delta y, and our units are going to be newtons. So that's the weight of each slab. Each slab is pumped a distance of 14 minus y, we decided. So we're just going to integrate from 0 to 10, 245, sorry, 000 pi times 14 minus y dy. And the way I always check to make sure I set my integral up is I'm going to say at the bottom when y equals 0, how far am I pumping my water? If I plug in y equals 0, I'm pumping at 14 feet. So that has to go clear to the top. At the top where y equals 10, how far do I have to pump that water? I have to pump it feet, I said feet, meters, 4 meters. So if I plug in y equals 10 here, 14 minus 10 is 4. So that tells me here at 10, that little disc of water is going to be pumped for me. So that tells me I've set my integral up correctly. Easy integral to evaluate, and we end up with, when we evaluate this, we get approximately 69272,118 joules. Questions? Setting up pumping problems like this. Not too bad to set up. Now, I don't have time to do an example of one, a different kind, but sometimes, depending on the shape of the container, your radius can vary as y changes. So if we had a spherical tank, the radius of our little disc is going to change. Or if we had a conical tank, the radius of the disc is going to change. You need to express the radius of each little slab of each little disc of water, or whatever the liquid is, in terms of y, because you're integrating over y. So when you have a variable radius, a different shaped tank, you have to find a way to express the radius of your little piece of water as a function of y. I can, if you would like, do an example of one where we set up a variable radius, record a video of it, and just post it so you guys can watch it over the weekend. Would that be helpful? Yes? Okay. I will do that. I'll do one with I think it's the same example that's in your book, but it's a spherical tank. So figuring out the radius, how the radius varies as the depth changes. All right, let me give you your homework. I'll post that. I should be able to get that done today and posted it. It'll be posted over the weekend. All right. There's my last page here. Homework. There you go.